So let me start from the top. We ended with I am just trying to revise first. Uh, with respect to the MDPs, I think so. We had completed till section 3.3, and we discussed a few problems there, exercises. Uh, uh, what we discussed was let me try to uh, take this. Mm, uh, we discussed the agent environment interface, in which this is the diagram of the interaction in a MDP. Uh, we have the estimate of the value and estimate of the action. Uh, based on that, based on those two uh, uh, classification, we have the either optimal action or the optimal policy. That's based on the optimal uh, action value pair. So there are two types. We will take a look at it in detail. So here the author goes through the MDP and the agent and what is the sequence or the trajectory that uh, particular MDP defines. This is example of a finite MDP. So here we take this, then the random variables that have discrete probabilistic distribution depends only upon the preceding state and action pairs. So that's the Markovian property that it holds. That's why a MDP. Uh, why do we use the terms agents, environment, and action instead of the terms like controller, controlled system, and a controlled signal? Because they are meaningful to a wider audience. We generalize it, and we focus on the attention to discrete time here, and the notations we have already seen in the uh, here. If I go quickly, the tabular solution, the summary of notation section. Here we have a complete end-to-end a list of all the Greek characters, uh, their peculiar, peculiarities. Uh, how is it referenced by for the first time uh, folks who are going through it, they may have some issues in trying to pick that up, but don't worry, we will take care of that too. Uh, then we in the equation 3.1, we had the sequence of all the trajectories that the state action reward, the state action reward, and yeah, that's the sequence. And this is a uh, 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 three tuple state action and reward. Uh, that's the way we define this. And the equation 3.2, we had the dynamics of an MDP, the P, uh, S prime R, that is conditioned on S and A, which this symbol gives the definition of the probabilistic distribution of this guy here. I think so. Everybody understands it. If not, please jump in. This is the dynamics as I've alluded to. P. This dot reminds us of the definition that follows from the previous definition. And this sign here means it comes from the notation of conditional probability. That means it conditioned on the previous distribution for the choices of st minus 1, the time step in the previous time step, the state of the previous time step, and the action of the previous time step. So this is it. Other than that, so anything else? Here we had a reminder of the specifics of a probabilistic distribution for each choice of S and A. So, how we define this. The MDP here gives this guy, ST and RT, that's depending upon the precedingly state and action pairs, as I've alluded to in the equation 3.2. Yep, 3.3 is for the continuous time domain. For the discrete, we can write here, we can replace this S by S plus, which denotes notation in the discrete space. This is the continuous space that we look at in equation 3.3. Next, we have the Markovian property, and we will take a look at approximation methods later. Then we had the 4 arguments dynamic function.
Hello. Okay, looks like Mayank just dropped off, right?
I think we lost him.
I guess he will come back soon, but let's wait just a couple of minutes and see if he comes back, and if not, we should probably proceed some other way, right?
Hey guys, sorry I dropped off. My computer, I think so is uh, jealous that uh, it crashed basically. So we try to. Uh, uh, I Yep, I think so. You guys can see my screen here.
Yep.
So I was going through. Yep. So I was going through this. I think so. I'm sharing my screen, right? Yep.
Yep.
Uh,
Yep. See it.
uh, okay. So this was the state transition probabilities in the equation 3.4 that I was looking at with respect to the three argument function. Uh, S prime that is conditioned on S and A. Yeah, the the reward, which is based on SA, the expectation of this guy. Uh, the equation 3.5 is the expected reward for the state action pairs as a true argument function. This is the reward that's based on the expectations. Um, yeah, this can be formulated as this term here on the right. Then we take a look at the equation 3.6, which is the three argument function, state action next state triplets. The expectation is again here defined as this. And then,
So I have a question here.
mhm,
Like, so typically, like, just looking at the state transition probabilities, right?
mhm,
I'm thinking about any like real world problem that I'm trying to solve using reinforcement learning. How do you
mhm,
even, how do you like, I believe that state transition probability should be defined under MDP, but you
mhm.
don't necessarily know that in advance, right? So how do you like know that, okay, this is the probability of transitioning from state S to all the future states? How would you know that beforehand?
That is dependent upon your environment, the environment dynamics. So, whatever kind of environment that you have, whatever the next consecutive uh, uh, possible states are in which an agent can go to, it's
Right.
defined on the basis of that.
Yeah, but like if I were to take a simple example, let's say I'm in the middle of a maze, right? And I'm trying to
Mhm,
find an exit. And I can
mhm,
actually move, take four different actions like
mhm,
north, south, east, or west.
mhm,
And so essentially, I can move into four different states, right? But how
mhm,
do I know what my transition probability is from my current state to each of the four states? I know that there are like four, like the next states I can move to any of the four states, but I don't necessarily know the transition probability, right?
mhm. Those transition probabilities are like this. I think so. You were referring to this example. It's the basic example that we will look at. Or let me try to cover this here because it will be easier. How do we know uh, the state values and the policies? Uh, so if uh, there are. Let me try to take it from the top here.
Sure.
And we will get to your answer in the, I think so that's the fourth section here in this article. So yeah, let me try to first um, try to answer your query, then we might proceed with the book. Okay. So
All right.
here the problem is of a baby robot which is lost in a mall, and uh, he has to get to an exit state to find his mom. And this uh, problem can be formulated with the environment that receives reward, and how it reflects its ability to accomplish some predefined goal. So uh, this is based on the uh, uh, what the agent takes an action on its performance, and those trying to modify those actions to improve that particular performance with respect to the policy and the value iteration methods that we will take a look at. Here, then they have defined it in terms of how do I say value problem, in which the state of the agent is evaluated. Uh, uh, this Let me try to view this. So this is the starting state, and this is the ending state. Uh, these are the rewards that we looked at. It's a simple kind of a +1 for going to the positive state, and the -1 for going to a state that's uh, uh, not acceptable for the path that it's trying to take. So it's totally depending upon the environment dynamics. So that I I think so. This was your query with respect to how we define our uh, uh, route that it
Yeah.
takes.
So yeah, I mean, I was reading this article, so I think like
Mhm.
typically my understanding of MDP is you need to define your state, action, transition,
Uh,
probability, and rewards, right? State
mhm,
I can see based on the current board or the maze situation. That's my state.
mhm,
Action, I
mhm,
know that I can go north, south, east, and west. I reward is something that I have defined myself. So in this case, in this particular example, the author has defined reward as -1, just so that
mhm,
the robot can reach the exit condition in the least amount of time. Because every time
mhm,
it's not reaching there, it's penalizing it by -1. So I understand
mhm,
that part. The
mhm,
part that it seems that is undefined is transition probabilities. And looking outside of this problem, even like to use RL for real world problem, um, I think I'm a little bit confused in terms of, do we even need transition probabilities to be predefined? Because you won't know that until you have the model of the environment, right? So that was a bit that part was a bit confusing to me. And in this case as well, like I don't think there was any mention about the transition probability, so didn't quite get it. Yeah.
Yep. You're right. If the environment is predefined, then we might need some sort of a how do I say it? Uh, Environment dynamics, but our agent can also try to figure it out in an online fashion with respect to the priors that are predefined from a separate environment. Separate environment here refers to the fact that uh, suppose our agent is trying to traverse Mars, for example, and those environment dynamics or the priors might be a bit different with respect to gravity and other things. But if an agent sees a rock on the right side of his camera viewport, then it has to move left to navigate through that. So those kind of priors can be used there. Those kind of priors can be learned from the environment on the earth and can be treated as mm, uh, how do I say it, a kind of a model based reinforcement learning problem in which your agent is trying to figure that stuff out. So yep, and that's one thing that can be done here. Yeah, I think so. You got my point of view, which I'm trying to make here. So that will be figured out.
Okay.
That's with respect to approximations that we may take a look later.
Sure.
But there are other approaches too. This is a I'm talking in terms of a very high level approach, but yeah, we might also take a look at that. I think so. From the high level perspective, you got my.
Yes, thank you.
Okay. Then what can we do is
Okay, maybe I can try to add on to this question regarding actions, states, and all this stuff. So the actions are determined by our policy. And the policy depends on the state we are currently in. And like generally, the policy is what we are trying to learn, right? So but the transition probabilities depend on our action and on the environment. And basically, that is what we are trying to learn during. So this Q function, which is a function of state and an action, and and we update it during the training. And there are different ways, as we will consider like later in the book. How can you like find good policy, and how can you determine the like so from this chapter, I guess what we need to take out that when you formulate the value function and Q function in this like recursive way, we can say, right? We have like basically we can determine a greedy policy becomes an optimal policy. Does it make sense?
Yeah, I think I understand the part, like in terms of like you have some random state values at the start and you know what your actions are and you know what your goal is. So you can do some trial and error, and you sort of converge to a point where your state values are optimal. And essentially, from there on, you just take your greedy action that leads to a state with higher value. And then you basically, that's your optimal policy. I think I understand that part, but I think my confusion is regarding when I was reading on MDP, and there it feels like in order to, like, RL problem themselves are formulated as an MDP problem, right? And if you want to solve, so in this case, we did not even think about transition probability. So his first question is like, is that even a prerequisite when I'm trying to formulate any problem under MDP? Like, do I need to have the transition probabilities, or is it something that we can ignore and work our way through to our optimal policy? And at that point, maybe we have some transition probabilities. So,
Well, in many cases, you cannot have transition probabilities before you explore your environment, right? Because the transition might be not deterministic. Like, so not every time a certain action leads to a certain outcomes. Sometimes it might lead to different, as shown, for example, in this diagram. So each action might lead to different outcomes, right? With some probability. And before you, if the environment is not known to you, before you start like your experiment, you got to learn those probabilities. Like you got to try some actions and to empirically find the probabilities of the outcomes of the actions, right?
Right. Okay. So is this like, is it fair to say that what you are describing is essentially like a model-free setup, because we don't know the environment or the model in this case?
So I'm not sure about this because I'm just following the course. I'm not an expert in RL, I'm really new as you are to this all. But so I guess the model based is referred to when you like learn a model of the environment, and model free is when you learn directly the value function or Q function, right? So
yeah, so because I think in the book, if I recall it correctly, and maybe if I'm wrong, others can correct me, but when we are using something like a dynamic programming, right? At that point, the model of the environment is known, and then we are just working our way to do the planning, right? Whereas if the model of the environment itself is not known, so that sort of becomes like a model free. So yeah.
well, like not necessarily. I guess the model of the environment might not be known to you, even in dynamic programming. If you look there, they consider like this iterative approach, right? But the difference between dynamic programming and the Monte Carlo methods considered in the next chapter, as I understand it, are the following. Like in Monte Carlo approach, you learn from the sample, like you do some action and observe the outcomes. And in a dynamic programming approach, you learn from the like expectation. So you got to take each action and like average across those to determine the value for a certain state. So yes, I guess maybe like if you unroll it this way, you got to know the environment to do dynamic programming, right? Because if you want to know the expectation of the value of certain state given an action, yeah, you get to know the environment, right?
Okay, thank you.
That's right. And usually the methods using dynamic programming, they are for planning. I think that's the difference. The other ones are learning. And for planning, you do no sampling because you already have a model of the environment.
Yeah, exactly. I think that was sort of like my understanding as well. If you have the model, which I think is what when you would use dynamic programming, so you can do planning. But in other cases, like for example, control, right? In that case, I think it's about like when you're trying to figure out what's the best way to, let's say if you're reaching, if you want to reach from point A to point B, then you don't know the way. That means you don't have the model. And that's where like in control problem, essentially it just becomes like when you're trying to figure out the optimal policy. Uh, yeah.
Exactly. We have to learn it by
Yeah.
interacting with the environment.
Seems like Mayank is having some issues, maybe.
Yeah, can someone
Yeah.
share their screen? So we might go through the rest of the chapters, the rest of the section of the chapter quickly.
I can share a screen
Of
with the
the
book if
books.
that's okay.
Yeah, yeah.
All right, can you see it?
Yep, yep.
Okay, good. So I will just...
Can you please give a quick overview of the chapter? Because unless we get to the problems, we need to get the basics here clear. So yeah.
So would you like me to like go over the chapter or maybe
The equations, basically we had gone through 3.4 and 3.5.
okay, so
you can take it equation by equation. Then we might take a look at the examples.
So have we considered these equations?
No, I don't think so. Yep, we have to get on to these. This is the fundamental property, I think so, with respect to the optimality of the policies and the value functions. Yeah, please go ahead.
Okay, so these are definitions. So here, what is the value function given policy so this defines a value function, and even value function as an expectation of the return given state S, right? And that may be viewed as a sum over all rewards, on all of the discounted rewards starting from this state to like here to we sum to infinity. Okay, so that's just a definition of a value function that which is an expectation of the discounted rewards given a policy. And here is an like similarly we can define Q function, which is an expectation of the returns given state and action pair. And equivalently, it might be reformulated as the sum over the expectation of the sum of the rewards starting from this state given action A, and again we sum to infinity in case of continual formulation. Okay, so now we here can see how this unrolls when we introduce some policy, right? So we move from the expectation given a policy. So basically we consider what does it means, and here it is a sum over all actions given a policy, and we sum over all possible states and all possible rewards. So this P of S prime R given S and A is, as we considered, it's transition probabilities, right? From state S given action A to state S prime and reward R. And so that's basically comes from the fact that this is an enrollment of expectation, right? We sum of over all possible S primes and R's to get the expectation of this value, and it would be a reward plus an expectation over next. You see here we have we define it in like recursively in terms of the expected return of this next state at the time t+1, and here we finally like write it in this recursive manner. We define value function of state S in terms of reward, sum of over all possible actions and all possible next states and rewards for the reward, and so we are given the reward and the discounted value of the next state. So again, this is a definition of policy. So, and we can look at this backup diagram. So when we are in state S and we have some policy pi here, and so say we have 3 possible actions, and each action leads to some other state and gives some reward R with probability P. So does it make sense? I guess silence is yes. Okay, and Mayank, would you like to go over this example? Okay, let's move further. Can everybody hear me?
Yes.
Okay, good. So maybe, and Mayank dropped off again, right?
Right. No.
Oh,
I'm back.
okay.
I'm back.
Nice.
Yeah. This is a golf example with respect to the value function of put. Here, PUT is defined as that. Yeah. We have terminal state that's 0 in the hole there. We make a put, and these states have values of -1, that is nearest to the hole, and there are we can see a kind of a terrain that's defined here by classification, which deterministically decreases as we move from the center to the outside. So that's the reward function of how this reward is particularly formulated. But then there is a sand trap too, which has a negative infinity. So putting the golf ball there might have how do I say it? Negative infinity. That's the our ball is stuck there. So they this example uh, uh, gives a viewpoint of, I think so they have solved it using 6 strokes to get from the tee to the hole by putting. So yeah, this is a kind of a uh, uh, how was it problem that is formulated here. So yeah, and the Wellman equation with respect to this guy here can be solved by an episodic task. Uh, it depends upon, I think so, the uh, state and the action pairs. Here, the open circle that represents the state, and the solid circle that represents the state action pair. So we can define it like that too, which with respect to the Bellman backup, sorry, the backup diagram that we have. So it tries to find the optimal action value function. Uh, so yeah, this is one formulation of a problem that uh, we can form. Yeah. And then in the exercise, I think so 3.17 and the 3.18, they try to uh, give the action values q pi s comma a in terms of the action values q pi next state next action pairs with the successors of the state action pairs. Yeah. Uh, uh, Here, the issue was, I think so, what's the Bellman equation for the action values that is for Q pi? So that's the action value function which we need to define for. Since it is analogous to equation in 3.14, uh, I think so there may be a couple of changes with respect to the probabilistic distribution of the environment dynamics. Okay. Uh, and we can form our and we can write our equation here. So there is a PDF that I had shared earlier, which has this, but we can formulate our own too. Uh, this was a similar problem with, so we were looking at exercise 3.17. Um,
I
So
guess it's quite straightforward to rewrite, right? We just substitute like according to the exercise, we get to substitute certain like q of SA would differ from v of s in a way that action is given, right? So we don't need to sum over all actions anymore because we have a certain action corresponding to q of SA, right?
Yep, yep.
in the equation, like 3.14 that we were just looking at, are we like considering both the straight transition probability and the probability of picking the action, right? So if you look at the first pi, I'm assuming that pi is the probability of picking the action in state A, in state S. And if you follow on, there's a small p. So that I am assuming is the state transition probability. from a given state S and action A. So we are accounting for both of these when we are thinking about like the value, finding out the value of a state.
Yes, agree with your formulation.
Okay.
So for example, like we can have a deterministic policy, right? And for each state S, we would have certain like action A. And in this case, we like sum over all A's would just correspond to a single best action, for example, right? Or we can have some probabilistic policy when for each state we can take multiple actions with some probabilities defined by this policy pi. And in that case, the value would be a sum of, or like weighted sum of over all possible actions. So
right. So this looks more like a very generalized case, like in the sense that if you are in a given state S and you can take a bunch of different actions, so that's why you have the probability of picking any action from those bunch of different actions, and that is where we see the first pi. And then like even when you have selected any given action, once you have already selected that, whatever probability that action might have, you still have like another probability distribution, which means that you can take that specific action and still reach multiple different states. And that's why I guess the second probability is coming into picture, where you have the state transition probabilities, right? The S prime could be like multiple different states that is possible of being reached having taken that specific action, I guess.
Yeah, so pi is like policy, and it depends on us, right? So we can determine our policy usually, I guess, and we can act as we wish. And P, it depends on the environment, and environment might be not deterministic. So given a state S and action A, we might end up in different, we might get different outcomes. And that's the transition probability distribution like considers that also.
Right. So yeah, I think that was one of my initial question as well, because if I have to calculate the state value of any state, let's say S, I would need to know what my transition probability is based on equation 3.14. I would need to know my reward. I would need to know my policy. So I think that's where I was confused, that would we already, is everything just random at the start, and then we go about finding the state value and converging at the true value of that state? Is that how you would proceed with it, or you have some defined way to do it as well? So.
I guess as Mayank alluded briefly, we can have some priors over the transition probabilities, right? So we don't have necessarily to start from the random distribution. We might have some priors, and it could still be valid like reinforcement learning problem. Say you can have like an model of your consider, I don't know, like robot moving in like I don't know, say it might be a car-like robot, and it drives along the way, and you can so you might model your state transition probabilities according to some physical model you can derive from the physics, from the laws of physics, right? But also you might have to learn to like improve over that, because your model might be not perfect. So
right. So this is like a constraint on knowing the model in the first place, right? When you're talking about defining, having some kind of priors, I would assume that you can only have priors if you know your environment, right? So that means you know the model.
Yeah, like in a maze, we don't have any priors. We just acting randomly, and we try to like accumulate the experience, right? Because that's the idea of a maze. We just don't know what waits us after the turn.
So in that case, you simply remove this state transition probability from this equation and then do your calculations. Is that correct?
Well, I guess you get to update your like the state transition probabilities would be a property of your environment, right? So say the environment outputs S prime and R for you. For example, in a maze, you might take an action and like step north, and the wall might be there. So we have like a blind agent for now, and he hits the wall. So the environment tells him that, okay, your next state is the same as it was, and the reward is -1, right? Or you can take a step north and get to the next grid box, and in that case, the role of an agent here would be to accumulate this experience and to build the mod. Like it might be, I guess, encoded in your queue function, right? So you will just you might not learn. So that would be in model-free approach. You don't try to build the model of the maze, right? You don't try like directly remember what the maze is, but you learn a queue function, which will tell you that don't take this action here because you will hit the wall. So these walls are basically encoded into your queue function, and you will have like a low value for the bad actions. So in this way, it still is model free, but we have to again we don't directly learn this state transition probabilities, but we like we learn a queue values for each state and action, and that would like help us to find the optimal policy.
Okay, thanks.
So let's move on to the next bit. So, okay, do we like linger on this exercises longer? So what's up here? We have this backpack diagrams, and
Yep. Back up diagrams, but we should discuss that intuitively how our equations should look like, or what our diagrams should be. Then we can go on to the next section or the next exercise.
Yeah, so I guess that if you want to see the equation, you can try to write it down yourself, or look to the PDF Mayank shared, and like compare your results. But it would be like kind of difficult exercise to do it vocally, right, in words. Yep. So we should probably move on.
But here with respect to the rewards, the R1, R2, and R3, we have kind of 4 parameters that form our AMDP. So this can be branched into a couple of equations, I think. And in the exercise 3.19, giving a intuition of what our equation should look like. This Q pi SA in the terms with the expected next report of the RT T plus 1. This can, since it's uh, uh, here it gives here it's written that this equation should include an expectation but not one condition on following the policy. So here, yeah, we can give a expectation here, uh, no, which is not conditioned on the policy, which is conditioned on the next reward. So that was one of my viewpoints here. Then the second equation writes out the expected value explicitly in terms of P S prime comma R conditioned on S comma A, such that no expected value notation appears in the equation. So that we can extend that based on the reward there, and we can uh, uh, write a parameter with that RT plus one expectation that I have alluded to earlier, and we might get the two equations based on this backup diagram that we have. Again, we will have to write it down and compare it with the previous. It might take 5 to 10 minutes, but yeah. If you guys are down for it, then we might write write it down. But we have to cover the code as well. So whatever you guys think.
Yeah, sure. Maybe we should write it down because I think that's like important to understand how this all relates.
Cool. So let's take 2 to 3 minute break, and we can write it down, and then we can compare our results.
Okay, cool.
Hey guys. I have a problem with the second equation, but yeah, easy to swap those terms out. So
All right, so should we like discuss this equation, or everyone is comfortable with this?
I think so we should discuss once.
Yeah, I might just open the document you shared, and we could have a look at it. I guess that would be the way to go about this. Okay. What would that one be? Which link should I follow? We shared it in Slack, right?
Yeah, I think so.
Could you share it in a chat right now? Because I cannot find it, I guess.
Yep.
Are you talking about the article?
No, not the article.
Is it this one?
No.
Okay.
This is one of the this is the solution to it. So I was thinking, how did we reach here? This is in latex, but yeah, it wasn't rendered. So
okay.
Because it is expectation in terms of t+1. So as they have alluded to in the next action state pair here, expected next reward rt t+1. So instead of rt, which we had at increments.
So yeah, I can reshare a screen with a rendered version of that equation just to know what we are talking about, right?
Yep, I try to look for that PDF again.
Yeah, I just rendered it here so we could see.
Okay.
So this is the equation I shared.
This might be the expectation of rt+1 plus the value function of the next day. So there might be a bit of errors, but yeah. And then the second equation is the value, which corresponds to the sum of r, and the second inner summation is the next state. So yeah, which depends upon the environment dynamics and return per time step multiplied by the discount factor of the next state pair. The next value of the state. This is it's a bit mingled, but yeah. The correct formulation will be.
I guess it makes sense, and that's what I was like getting just by rewriting the stuff from 3.14. So hope this makes sense to everyone. If not, or you got different answer, please like jump in now and ask your questions or introduce your opinions, please. Just as I opened it, right? Yeah, go on.
No, I was just saying that this makes sense for sure. Yeah.
Okay, cool. So just to, as I opened this document here, I was playing with that example from the recycling bot, and I just wanted to like get a feel. So these are symbolical. So this part I shared after the previous week. This was a symbolical solution for the grid word problem we had there. I think this looks familiar. So this is a solution under random policy. And so I guess it just, if you have some trouble understanding all that stuff, you should probably go on and write down these equations. I didn't do it actually because I just like generated those with a simple loop, but yeah, and I wouldn't recommend do it for the grid world because it obviously contains all this bunch of equations corresponding to each state here. But for the recycling bot, we have only two possible states. So the value function would contain two equations, right? And here is like, we can try to unroll this formula to see how it relates to what we had for that example. So do you remember the example with recycling bot?
Could you please give an overview for everyone, because I think so.
Yeah, sure. So okay, let's just let me share again as a book, and that should make things simpler. All right, let's get to the, I guess it was somewhere over here, right? So we have this table and diagram for, and it specifies all the possible states, action, and transitions possible from each state action pair, right? So if you remember, so we have a recycling bot which can like do three actions: search, wait, and recharge. And it can be in two possible states, which correspond to high battery level and low battery level. And for each state action pair, we have possible two possible transitions, which are parameterized by these probabilities alpha and beta. And for some state, we have like deterministic transitions. For example, here, when we have a high battery and we wait, we will end up with high battery, right? Because we don't use the charge. And we have corresponding rewards associated with each state action next state. Like with each possible transition, we have associated rewards. And here we have like one number for a reward for search action and reward for wait action. And we get negative reward of -3 for the case when we tried to search but ran out of battery. So we are in a state when we are like down and someone got to recharge the bot, right? So that results in negative reward. So Okay, does everyone get like overall feeling? So what's the problem we're dealing with? Hopefully, yes. Let me check the chat. Okay. Okay, so now I'll get back to that small simulation, we can call it, right? Yeah, not a simulation, but a solution. So here I have this is just variables we can control. So this is a discount factor gamma. We have two like probabilities which parameterize our transition function, right? Alpha and beta. And we have some rewards for searching and for waiting. And reward for waiting should be lower than reward for searching, right? So we reward a bot for getting some garbage, and it can definitely get more when it's searching. So, okay. With that, we can solve that. We can find an analytic solution for that, for the value function for that problem. But as it was mentioned before, you got to have some policy. So each value function is associated with some policy. It doesn't make sense like when it's detached from it. So here is the solution for random policy. So this is this equation corresponds to the value for high state. And in high state, we can take two actions. And under random policy, it would result with two actions with probability of 1/2, right? So hopefully that makes sense. And with probability of 1/2, we take an action, search. So we get the reward. This is an expectation of a reward for searching. And also our value function would be determined by this reward plus a discounted reward for the value of the next state. And the value of the next state, it's like recursively defined here by weighted sum, like it's a linear combination of two possible next state values for next states. It's here it's v high and v low. Okay, and the same is for weight, but here it's kind of simpler because when waiting, we can only get to the high state. So that's how we translate that table into an equation we can solve to get the value for that particular state. And we have this value. This is a constant. This is a constant. Gamma is a constant. Alpha and beta are like also parameters which are defined by the environment, right? So by their by the way how our bot operates. So basically that would be like this alpha and beta would encode the properties of our battery. All right, and the same here is done for the value of low state. And again, you can unroll here we can take two, like not two, but three actions. And the actions are search, wait, and recharge. And when recharging, we don't get any reward, but we get from low state to high state. So here the like value reward would be 0, but we also add an expected reward for the high state, right? And this problem can be formulated in two ways. Like as a continuous task, right? Or continuing task. And in this case, here, when we go from low state and we are down, so the robot is completely uncharged and it cannot move, we add this, we still add this reward for a high state, because like somebody takes us back to the initial to the high state, and we continue going, and still the ideally robot should learn that, okay, I don't want to be in this state anyway, right? But to consider it as episodic task, we got to remove this component here, and that would be a terminal state when when our value does not depend on the next state because we terminated. Okay, and one interesting thing you can look at. So here is a solution here, and when we define this problem as a continuing task and set discount factor to 1, which means no discounting, there is no solution, right? And I think it should make, if you understand all this framework well, it should make sense to you, because our values in this case are undetermined, because we define it recursively on itself and we do not discount, so our solution does not converge to certain values, right? Because we actually in a limit we get infinity. So, but if we remove this component and we have an episodic task, we get a solution, some concrete solution for this problem without discounting. Okay, does it make sense? All right, so in this chapter, we do not talk how we determine this. So these values are a product of our policy, and here it's a random policy. And in the next chapter, we will go into details. How do you find an optimal policy, right? But here we just want to have strong understanding of the formulation of the problem, right? But we can explore a bit here. So I got some error here, but okay. So here you can consider I change, I vary, let me show the code. I vary the probability of searching when you're in high state, and from low probability to high probability, and yeah, so I'm getting something. I guess I got it broken. Maybe it doesn't work for. Probably I get to add the discount here and get back this component here. All right, yeah, and okay, so now it shows what it's supposed to show, and here you can see that with increasing the probability of searching from high state, we have higher value of that state. So that would correspond to the fact that when you are charged, you want to search, right? And that aligns well with this symbolic solution for the value function. And here on the contrary, when you search in a low state, you might expect to get lower rewards. And that depends on these values here. You can play around with it and get different, slightly different numbers. And also it depends on the rewards we have for searching and for so here, as you can see, when we set the reward for search and for weight to be the same, actually value function for searching drops because when searching we will eventually go to the low battery state, and that low battery state has a lower value, right? So that's how you like can interpret all this mathematically, and but on the other hand, you just can get a feeling how this can become really infeasible to find this solution. So we have very simple problem. This is a grid world of like 5x5 grid, but already we got to make up this, and again, this is for random policy. We get to make up this bunch of equations, and yeah, so that's already something you probably don't want to do like with pen and paper, right?
Yeah, totally agree.
Okay, so let's go back to the book, I guess. Right. So we were at the end of 3.6, right? And
so we have solved the grid world with respect to the 3.2, right? The problem that example defined.
Yeah, so the
3.3, if I'm.
Yeah, so they're you see, like my numbers are correspond to this solution, which is for random policy, and further down they give you a solution for optimal policy, and you have much higher values there.
Yep. But the actions there are different too. So
yeah. So we will have, in that case, we will have to like edit our equations to depict our policy there. So as you can see from this bit here, we try to determine the expectation of a policy, and yeah, so probably that. And to solve for optimal value, you need to incorporate an optimal policy to your solution, right? So you got to maximize our policy.
So it's with respect to the maximization of it's not iteration, it's maximization.
Yeah,
that's cool.
Okay, so here we can go through these equations, right? So the optimal Q values would also correspond to the maximization of over policy of Q pi. And here this is like like we unroll this with respect that our optimal Q values depend on optimal, like are might be written in terms of expectation of the reward and optimal value for next state, right?
Yep, totally.
Okay, and here's the way we can write down this for optimal values. So So that would be like we try to maximize expectation of the sum of reward and this return, discounted returns for the next stage, given an optimal policy here, right? So now we compute the expectation under optimal policy in contrast to what we did before when we just considered any policy. So that, and in this way, basically, I guess what we got to take out from here is that when you have an optimal policy, or when you have an optimal values computed, you can take a greedy policy because the best value for the next state will optimize the best value for all state of all next states are incorporated into the value in current state, right?
Yep, since it's using the max of, yeah, so it's the max operator. So yeah.
Yeah, so that is a really like that is what really powerful about this formulation, because if you like know that generally greedy algorithms do not result in optimal solutions. They might end up in like locally optimal solution. But as we define our value of the current state in terms of the expected value of the next state with discount factor, we actually, our greedy policy will be optimal policy, and that's really important for this kind of tasks, right?
Yep, and plus the rollout factor is also kind of matters in the terms of how we are trying to use it empirically, such that the number of iterations are at each time step are within a particular constraint. So here, how we choose our hyperparameters with respect to the time, the rollout, and the expected the expected backup diagrams with respect to it can be a kind of a TD based temporal difference based in which our next state rollouts are trying to uh, how do I say it? Uh, uh, Narrow it down, or they are trying to give a max with respect to kind of a SARSA approach, which we will take a look at in the future sections. So yeah, that was some extra sauce. Thanks.
And here you can see this backup diagrams for the optimal value function and Q function. And yeah, so the difference here, and as the same as you can relate it to the equations. So here we have this max operator like in front, and you can see that we for optimal value function, we take a max over actions from the state. And here you can see that you got to take like max of over actions from the state S prime, because we are given the action A for the state S, right? So that's kind of small difference in formulations, but those are like equivalent.
So I have a
Yep.
Yeah, sorry, I had a question. Like looking at equation 3.19, it seems like we have the optimal value function. So from that, we can figure out the optimal policy, just which in this case is the greedy policy. So And then 3.20 is like we are not thinking in terms of state value function, but we are thinking in terms of action value function. So is it like fair to say that once you have the optimal state value function, then essentially you know what your optimal action value function is, which is basically your greedy policy. Um, is that correct to say that?
No,
Because,
I don't think so. Because the dynamics here depends upon, as we have seen an example from the slides, and earlier, I think so, that was from the slides of uh, that example that I have shown. Let me try to with respect to the sleep cycle and uh, hub and all student that goes to a class. So that totally depends upon not only the value states but the action pairs too. So it depends upon how our problem is formulated there. So yeah, you cannot assume it based on that.
I guess we will get into details of that as we progress with next chapters, and that would be much clearer when we will go to solving, like actually solving problems. And so all right, I guess we are getting to the end of the chapter, right? So here we can have a look at the solution for the grid world problem. So here we have an optimal policy and the value function which correspond to that policy, but we like don't know yet how do we get to that solution. And again here we can look at these equations for the recycling robot. Okay, I haven't looked at this much, but I think that should correspond to what I was showing you in that notebook, roughly, right? And here they solve for the optimal policy and or not optimal policy, but optimal value function. And here it is determined like recursively. So this is an solution. So optimal value for high state would be given by like maximum possible value of these two equations. And again, we have three equations for low state because there are here we have three possible valid actions, and here we have only two possible valid actions we got to consider. So I hope that makes sense.
Yep, and I think so. You defined a similar kind of formulation in the examples that you just gave. So
yeah, but going from adding this max operator would mean that we get to this. So it becomes a system of nonlinear equations, right? So when we solved for certain policy, we had a simple system of linear equations, right? it's trivial to solve mathematically. But when you introduce this max operator, it becomes already a bit more complicated in terms like of finding the solution, right?
Yeah, kind of, but it depends upon the implementation too. So, and rollout with respect to how much we want to uh, 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 since it is optimal, so we will have to go through each and every state of action pairs. Here, the value of the state dynamically, but yeah, I think
So that would be next chapter, topic of the next chapter, right? So
yeah.
Yeah, but I mean that that is basically the motivation behind using dynamic programming. So it is easier to solve it iteratively by updating by doing a like couple of rounds of updating value functions rather than solving it like trying to find the solution for this system of equations, including the max operator, right?
Yep. But wait, in the end, we between theory and the empirical evaluations, we are always faced with some kind of a probabilistic distribution that we have to pick with respect to finding the computational trade-offs. So, in the end, the limitation of our compute matters. Or if we have a quantum chip of it, then there is no issues though.
Yeah, and I guess we are running out of time, but you can quickly look at this bunch of exercises. So draw or describe the optimal state value function for a golf example. I guess it would be easier to do when you look at the example. And if no one wants to jump in and just communicate these solutions, I guess you get to do it on your own.
Yeah, but it will be fun to kind of share what we draw up and maybe homework for this week. Exercises 3.20 to 3.29. There are 9 uh, equations, 9 exercises that we might give it a try.
And like these exercises are quite straightforward and quite similar to what we did before with that equations 3.13, but this time you got to deal with the optimal values. So you would have to formulate, say, optimal value function in terms of optimal state action function, right? But in general, that should be like quite straightforward because there are direct correspondences here.
Yeah, earlier we tried with the normal or not optimal policies. Now we are trying it the same with the optimal policies. So that's the major difference here.
Yeah, and in this section, the authors go into this introduce us to what we will be dealing with in the next chapters. So, and basically that in a general case, we cannot find exact solution for the optimal value function or optimal policy, but we got to go with approximate solutions. And yeah, and basically that what we will do throughout the rest of the book. So all right, I guess we are done with this chapter. So please ask your question if there are any remaining, and share your thoughts if you got something.
Yep, and just a heads up, we might not be totally correct on all accounts that we have shared our thoughts on. So take it with a grain of salt. And since we are not experts or doing PhD in this subject, so we might be a bit off. So yep, we are just a learning group. So yeah,
Yeah, definitely. If you
do
find some
not
corrections, just
please,
post
yeah.
it. All right.
So are we going,
Yeah.
are we
Go
going
on.
to go to chapter 4 the next week? Or
Yes,
what's
the
the plan?
half part of the chapter 4, the policy evaluation, policy improvement, policy iteration. I think so. I will update that in the sheet as soon as I have access.
Sure.
We will.
Yeah, that'll be great. Thanks.
Yeah. Other than that, this is a very important chapter since it gives the basic formulations for an MDP. Uh, so it's kind of like, how do I say it, the foundation. And maybe if you guys haven't gone through the David Silver's lecture on MDP, please go through it. The questions that uh, we are trying to solve will be answered. So yeah, that was one thought. I will try to give a viewpoint up on. Uh, I think so. You guys can share my can see my screen, right?
Yeah.
Yeah. So this was kind of an example with respect to the Bellman expected equation that I think Sankalp asked with respect to the value function and the action value function, the state value and the action value. What's the difference, and can the similarity be does one does finding the optimality in one uh, always means the uh, getting to an optimality to the action value too? That's not always the case, because uh, this is a kind of an intuition on the abstract representation of why this is. So uh, this is the state value here. It's represented as this, and this is represents the action value, and this is your uh, value of the states here, which is the summation of this guy, and the expected equation for the Q, that's the state action pair, is this. So you can see the difference in the formulation on what it depends upon, and to give a concretization with respect to if we have multiple states, this is how you define it. The summation term here, which comes before it. And the next is the Bellman's expected equation for the state action. So this is how this expands further. And to give an empirical result, I think so you guys can see this. Going to the pub, Facebook study, and this example, this is the example that I was referring to, in which if you try to calculate this is what you get. This is specific from one end to the other with only the value formulations, the state value, and here is optimal value, and the other one was the state action value. So it depends upon the reward formulation here. So and the that's the how does it mm, the return of the previous states. I am a bit all over the place right now, but yeah, I think so. Yeah, these are the differences, and if you go to the lecture here, you might be able to easily get what I am trying to get to. So, yeah, these are the equations. Yeah,
Cool.
thank you.
All right. Thanks, everyone. Bye-bye.
Bye, guys. Take care. We will meet again next week. Same